Hello. Today we shall talk about a very important mathematical function. This is the natural exponential function, which we define as the inverse of the natural logarithm. Here, to remind you that the natural logarithmic function ln x has domain of the logarithm all positive numbers, the range of the logarithm all the number line, and the logarithm is 1 to 1. The derivative of the logarithm is 1 over x. When x is positive, this is strictly positive. The logarithm is increasing everywhere on the domain, so it's 1 to 1. So we define the natural exponential function. I shall write exponential y equals x when y equals natural log of x. So I want here briefly to remind you the basic relations for one function and its inverse. Basic relations for general notations: f of f inverse of y equals y for all y in the domain of the inverse, which equals the range of the original function. Also, f inverse fx equals x for all x in the domain of the original function, which is the range of the inverse. Also we have the inverse of the inverse is the original function. These are basic relations which are true for every pair function inverse. In the case of the natural logarithmic function, when fx equals natural log x, how these look like? We have the first will be natural log exponential y equals y for all y which are in the domain of the exponential function, which are all real numbers. Also exponential logarithm x equals x for all positive x. Also, the exponential function is written this way. Exponential x is written like power, and in this case it depends on the circumstances. If this is more convenient, we write it this way. The natural relations take this form: natural log exponential y equals y, and exponential to power natural log x equals x. So these are basic relations shortly connecting the logarithm and the exponential function. Also, remember that natural log e equals 1, and then the exponential brings 1 to e, so exponential 1 equals this number e, which actually we can write this way, and also logarithm 1 equals 0, which means exponential 0 equals 1. Now the laws for the logarithm correspond to laws for the exponential function, and we have these laws or properties. Exponential a plus b equals exponential a times exponential b. Whatever a and b, all a and b, because the domain of the number line. Exponential a minus b, that's actually ratio of exponentials. And if you have exponential x to some power, let's say n, this is exponential nx. These result from the properties of the logarithm. And it's something familiar from algebra. We know that x to power n times x power m, this is x n plus m, and that's the same property that we have here. Also, if you have x power n divided by x power m, this will be x n minus m. And if you have x power n to some other power m, you just multiply them like that. So there's nothing special here. You have seen also this property, x to 0 power is 1. So the exponential function behaves like normal exponential. However, it has some very, very special property, and that's why we are using it. We're not using 2 to the x or 10 to the x or something like that. We're using e to the x because of this very special property, the derivative. What is e to the x prime? To compute this derivative, we shall remember how we differentiate the logarithm. So here again, logarithm x prime, this is 1 over x. And if we have a composition, logarithm u is a function of x, differentiating this by the chain rule, we have u prime over u. And now we shall take one of the basic relations. Let's say we write natural log e to the x equals x, and u will be the exponential function. So we differentiate now this equation with respect to x. We get logarithm e to the x, all this prime equals x prime. And on the left side, this will be e to the x prime over e to the x, u prime over u. On the right side, x prime is just 1. And then from this simple equation, we see that e to the x prime equals e to the x. A remarkable property. The function is the same as the derivative. This is the only function in the world that has this property. That's why the exponential function is so important. Later we shall study, very soon actually, other exponential functions. For instance, we can take the function y equals 2 to the x. It does not have this exact property. The derivative of 2 to the x will be 2 to the x times natural log of 2, which is something quite different. It's not so convenient. Anyway, after learning about this property, we had to see how to differentiate composition. If we have e to the u, how to differentiate? We differentiate with respect to u, deu du, then du dx, of course. And this will be e to the u. It stays the same here in the first factor, and du dx is u prime. So here I shall write this again. Deu dx is u prime e to the u. So that's how we differentiate a composition. I'm writing here u prime first because it's more convenient in many cases. Now, I want to do some examples from the book. Starting with something very simple. For instance, example 2b. Remember, we have section 6.3 star, darker pages. In 2b, we have to simplify natural log 1 over e squared. We simplify it this way. Natural log 1 over e squared, it's a logarithm of ratio, so I'm writing natural log 1 minus natural log e squared. Logarithm 1 is 0, and for the second term, we put the power in front using the exponential property, so this will be 0 minus 2 natural log e. Natural log e is 1, so this is just negative 2. Another example, let's do 4a. Again, simplify natural log exponential sine x. Well, just using the fact that logarithm exponential are inverse to each other, this is exactly sine x. You can put everything in the place of sine x, natural log exponential whatever equals this quantity. It can be x, sine x, anything. So that's very simple. 6a. Solve for x this logarithmic equation. Natural log x squared minus 1 equals 3. We're solving logarithmic equations taking exponentials of both sides. Many people have seen this in algebra. And taking exponentials of both sides, I'm writing exponential logarithm x squared minus 1 equals exponential 3, taking the natural exponential function. On the left side, this is x squared minus 1, and this equals e cubed. From here, x squared equals e cubed plus 1, and x, of course, will be square root, don't forget plus minus, e cubed plus 1. Now stop for a moment. And can we take both plus and minus? Yes, we can, because in the logarithm, in the problem, it appears, x squared appears. When you take x squared will be something positive, everything is fine. So plus minus will give you two solutions. Okay, let's see number 12. Again, solve for x in this logarithmic equation. Natural log 2x plus 1 equals 2 minus natural log x. Before solving the equation, we had to look here carefully to see what x are acceptable. Since we're writing logarithm x here, this requires x to be positive. And from this position, 2x plus 1 should be positive. X should be bigger than negative 1/2. Well, if x is bigger than 0, it's bigger than negative 1/2, so this restriction remains x positive. What next? We have two logarithms. We bring the second logarithm on the left side, and we write natural log 2x plus 1 plus natural log x equals 2. The two logarithms we can put together. Logarithm product is the sum of logarithms. So this is actually a product, logarithm 2x plus 1 times x, all this is inside the logarithm, equals 2. And then we take again exponentials of both sides. Exponential logarithm here, I can multiply inside, it becomes 2x squared plus x. So let's do it. Let's do it this way. So we get logarithm 2x squared plus x equals e squared. On the left side, 2x squared plus x equals e squared. And then we have a quadratic equation for x. 2x squared plus x minus e squared equals 0. Using the quadratic formula, x will be -1 plus minus square root 1, and becomes plus because I had to write minus for AC, and because this c here is negative, becomes plus. And 4 times that's 8 e squared over 4. Okay, and now remember we have this restriction, x has to be positive, so we have to take with plus only, and here is the answer. -1 plus square root 1 plus 8 e squared over 4. This will be a positive quantity because this radical is bigger than 1, obviously. Okay, download number 12. Moving further. Now let's do some limits involving the exponential function. I'm jumping to number 30, and here we have to compute this limit. Limit exponential 3 over 2 minus x when x approaches 2 with minus, which means from the left. X is less than 2. To compute this limit, we have to see what happens with 3 over 2 minus x. We have first to compute this limit when x approaches 2 from the left. When x approaches 2 from the left, 2 minus x is positive. However, denominator goes to 0. So all this will be infinity. And I can roughly say this is exponential infinity, which is infinity. The exponential function grows to infinity when x grows to infinity. Let's write this limit here clearly. Limit exponential x when x grows to infinity is plus infinity. Symbolically. Because infinity is not a number, this simply means that e to the x grows more and more, becomes greater than any preassigned number. Actually, the function e to the x grows very fast, and that's why people talk about exponential growth. Growing like the exponential function, very fast. To confirm this, I shall sketch the graph here. When x is 0, the exponential function is 1. Then the graph looks like that. It becomes steeper and steeper. Y equals e to the x. On the left side, when x goes to minus infinity, the limit is 0. Here it is good to mention a very important property for one function, for the graph of one function and the graph of its inverse. This is the relation. They are symmetrical according to the axis y equals x, the bisector of the first and the third quadrants. This property I want to mention here now. So let's take the coordinate system. And here we take the bisector y equals x in the first and the third quadrants. And suppose we have some graph here, found function y equals f of x, which is 1 to 1. Let's say like that. Then the graph of its inverse will be symmetrical on the other side of the bisector. It will be like that. This will be y equals f minus first of x. And now remember the graph of the logarithmic function. When x is 1, it's 0. And it goes like that. Y equals natural log of x. Now let's do the bisector here. And the graph of the exponential function, it will go to the point 0, 1. And it will be like that. Quite steep. Okay. So this is about limits. Now I would like to practice some derivatives, but I think this should be in a different lecture because this recording becomes very large. And so next time, derivatives.